devastating force of nature we as inhabitants of Earth faced in the past and will continue to face in the future. Earthquakes account for more than 50% of death and damage that occurred on our planet due to natural disasters. Collapsing buildings, other man-made structures, and landslides are mainly responsible for loss of human life. If we look at our planet devoid of oceans, we can see that it is scarred all over, with ridges, mountain ranges, canyons, volcanoes, and other physical features. While some of these physical features can be attributed to surface forces like wind, river flows, receding glaciers, ocean currents, etc., majority of them can only be explained through our understanding of forces that emerge from within the Earth's interior. Over the years, the scientists have made it their quest to understand and explain the interior structure of the Earth and the forces that play within it. They inquired into rocks, seismic waves from earthquakes, volcanic activity, and sonic wave propagation inside the Earth and evolved the Earth's interior structure from their findings. If we look at a cutaway section of our planet, we can see that its interior is divided into four main layers: the crust, the mantle, the outer core, and the inner core. The outermost layer of the Earth is the crust. Crust comprises of continents and ocean basins. The crust has a variable thickness. It is 35 to 70 kilometers thick beneath the continents and 5 to 10 kilometers thick under the ocean basins. The main composition of crust is aluminosilicates. The layer beneath the crust up to a depth of 2,900 kilometers is called the mantle. Oxygen is the single largest element in the constitution of the mantle, followed by silicon, magnesium, iron, aluminum, calcium, etc. These elements cohabit the mantle in their oxidized form. Temperatures in the mantle vary between 600 degrees centigrade to 3000 degrees centigrade, while its density varies between 3.38 to 5.56 grams per cubic centimeter. These variations are believed to be in proportion with the depth of the mantle. The mantle is further divided into upper mantle, transition zone, and lower mantle. The outer core is 2,300 kilometers thick. It is in liquid form. The outer core is believed to primarily contain iron-nickel alloy with about 10% sulfur. The inner core is almost entirely composed of iron. Temperatures here are around 4,300 degrees centigrade. Despite the high temperatures, the inner core is believed to be solid. The crust of the Earth, along with topmost solid portion of the upper mantle, is called lithosphere. Lithosphere floats on partially molten plastic layer in upper mantle called asthenosphere. Lithosphere is not seamless. It is cracked in several places. These cracks connect with one another and close to form distinct plates of different sizes which float on the partially molten or plastic asthenosphere. These plates move in relation to one another and cause abrasions on the margins. The large-scale motion of these plates that constitutes the lithosphere vis-a-vis the forces of the Earth's interior is described as plate tectonics. The crust of the Earth can be divided into 30 tectonic plates. Major plates are shown in this map. These plates are at perpetual motion in relation to one another as indicated by the arrows depicting the direction of motion. Over 200 million years ago, all the continents of the world were clubbed together in a massive landmass called Pangaea. Pangaea then split up into continents that we know today. Over the eons, these continents moved to their present position. The Indian plate broke away from the southern landmass and moved up north by northeast to collide with the Eurasian plate. The collision of the small Indian plate with the large Eurasian plate resulted in subduction of Indian plate beneath the Eurasian plate. The resultant physical feature along the line of collision is the rise of the Himalayas. The Indian plate continues to push and subduct beneath the Eurasian plate to this day at the rate of 5 centimeters every year. Let us understand the forces beneath the earth that are responsible for the movement of the plates on the earth's surface. Scientists believe that the phenomenon of mantle convection is responsible for the movement of the plates. The lower mantle receives large amount of heat from convection in the inner core. Decay of radioactive elements in the mantle and the crust also contribute to this heat. According to the second law of thermodynamics, this heat must flow to a cooler place. Thus, it rises up towards the cooler areas near the surface. If Earth were smaller than its present size, this heat would have flowed to the surface by conduction and radiated out. But because of its current size, a substantial amount of heat flows towards the surface through convection. Heat-carrying particles rise to the surface, lose heat and sink down again to gain heat and rise up. This takes place in a continuous fashion to establish convection currents beneath the plates. The direction of the convection current will determine the direction of the plate movement. All the 30-odd plates that constitute the surface of our planet have distinct boundaries. In accordance with the relative movement against one another, plate boundaries are classified into 3 types. They are the divergent boundary, the convergent boundary, and the transform boundary. Divergent boundary is where the plates move away from each other. Here, magma rises from the deep to fill the gap, forming a ridge along the plate boundary. Example of divergent boundary is the Indian Ocean Ridge, where the Indian plate moves away from African plate in northeasterly direction. Another good example is the Red Sea Ridge, where the Arabian plate is moving away from the African plate. Convergent boundary is exactly opposite of divergent boundary. Here, the plates move towards one another from opposite direction. On collision, one plate subducts beneath the other. Distinct physical feature on convergent boundary is either the presence of fold mountains or deep trenches. The Himalayan mountain range on the northeast of India resulted from subduction of Indian plate beneath the Eurasian plate along the convergent boundary. Transform boundary is where the plates slip past one another in opposite direction. San Andreas Fault in California, USA, where the Pacific and the North American plates slip past one another, is a well-known example. Closer to home, the Indian plate slips past the Arabian plate on its northwestern boundary. Several faults exist in this region, which is identified by seismologists as the Irwin Fracture Zone. At plate boundaries, tremendous stresses build up and strains the rock. The accumulated strain amasses potential energy. When strain exceeds the threshold capacity of rocks, it is released. This results in an earthquake. The constant movement of earth plates strain the rock and fractures them at various places. These fractures are called faults. Faults usually appear near the plate boundaries. They are weak spots on the plate and tend to act as vents for release of energy from within the earth and cause earthquakes. The rock faces along the fault line differ in their strength. The sturdier face is called footwall block and the weaker face is called hanging wall block. Fault behavior depend on the plate boundaries. At divergent plate boundaries, the fault blocks tend to slip away from each other due to crustal extension. This type of faulting behavior is called normal faulting. At convergent boundaries, the fault blocks tend to slip onto each other due to crustal shortening. The hanging wall of the fault protrudes onto the footwall. This type of faulting is called reverse faulting. At transform boundaries, the fault blocks slip past one another in opposite direction. This type of faulting behavior is called strike-slip faulting. When the accumulated energy is released along the fault line, the earth shakes with convulsions and an earthquake is felt in the region. The point below the earth where the earthquake's energy is released is called hypocenter, and the point directly over it on the earth's surface is called epicenter. The energy is released in a series of waves called seismic waves. These seismic waves are responsible for the shaking and convulsions of the earth during an earthquake. Seismic waves are classified into body waves and surface waves. Body waves travel through the inner layers of the earth, while the surface waves travel through the upper crustal layers of the earth. There are two types of body waves. The first is the primary wave or P wave. This is the fastest wave and its effect is first to be felt during an earthquake. P waves are longitudinal waves. They are powerful waves. They can pass through solid rock and fluid layers. They push and pull the medium as they travel through it. Their effect is similar to that of the behavior of a spring when it is pushed and pulled. The direction of push and pull is same as the direction of the wave. P wave is closely followed by the second body wave called secondary or S wave. This wave can only pass through solid medium. It is responsible for the side-to-side shake of the earth during an earthquake. S wave is a transverse wave. When it traverses through a medium, the particles vibrate perpendicularly to the direction of its propagation. The effect of this wave is similar to waves created when a flexible string is whipped up and down. Surface waves are of two kinds. They are Love wave and Rayleigh's wave. They are named after scientists who explain their nature mathematically. Love wave travels along the surface very fast. It shakes the ground from side to side laterally as it passes along the Earth's surface. Rayleigh's wave, on the other hand, is slower than Love wave and follows it along the surface. It rolls the ground particles as it rumbles on. Earthquakes send seismic waves in all directions. Body waves, such as P and S waves, travel a curving path through the Earth. As a result, they arrive at seismic stations from below. P waves cause temporary microscopic deformations of the Earth in the direction of the wave motion. Here, energy is primarily recorded on the vertical component of the seismogram, with less energy recorded horizontally. By contrast, S waves cause deformations perpendicular to the direction of wave motion, resulting in predominantly horizontal or back and forth motion. Here, less energy is recorded on vertical or up and down component. The slower surface waves such as Love and Rayleigh's waves move in a complex angulating pattern. They show up on all three components, leaving a more dramatic record of the bigger earthquakes halfway around the world. The Indian subcontinent is divided into 4 seismic zones by the scientific community. These zones are identified by zone number 2, 3, 4 and 5. The earthquake vulnerability factor increases with zone number. Thus, zone 4 and 5 are at maximum risk of experiencing large magnitude earthquakes. The northeastern part of India is the collision zone between Indian plate and Eurasian plate. Here the seismic activity is very high. Therefore, this zone is classified as a high-risk zone for earthquakes and has experienced several tremors in excess of 7 magnitude in the past. Loss of life during an earthquake is mainly due to collapsing buildings and other man-made structures. Therefore, in the vicinity of epicentral zones, buildings and other structures must incorporate technologies which are resistant to seismic activity, ground motion, and soil failure during earthquakes. Even the existing buildings can be made more earthquake resistant by seismic retrofitting and bracing techniques. People living in high vulnerability zones must prepare and keep a survival kit handy at all times to deal with earthquakes. The survival kit must contain a torchlight, portable wireless radio set, batteries, bottled water, first aid kit as advised by local doctor, non-perishable or long-life packed food. This kit must be checked every 3 months and expired items like batteries, food, water, etc. must be replaced. The flashlight and radio set must be tested to ensure that they are in good working condition. Updated kit will be a great help in the event of an earthquake. If you are indoors in the event of an earthquake, you will be in danger of injury from falling objects, shattering window glass, falling ceiling plaster, etc. Therefore, it is advisable to stay away from cabinets, almirahs, closets and windows. Seek refuge under a study table to avoid being injured from shattering or falling objects. At the first respite, you are advised to leave the house and walk to an open area like playground, parks, etc. so that you will be safe from possible shocks that precede or follow a main earthquake. If you are in a crowded public place, stay calm. Do not panic and stampede. Follow protective advice given earlier. Leave the premises in an orderly manner. If you are outdoors during an earthquake, avoid being near electric poles or transmission wires. There is a grave danger of electrocution or injury from snapping and falling live wires during earthquakes. Do not stand near buildings and under signboards. You will be in the way of falling objects and get hurt in the process. It is necessary to take certain precautions after an earthquake. Fires usually break out in their aftermath. Therefore, it is important to secure fire hazards. In this regard, you are advised to switch off electricity and prevent fires from short circuits, to shut down gas stoves and other open flame appliances, to secure kerosene and other flammable liquids. Amongst other safety measures, you are advised to wear sturdy footwear to avoid damaging feet on scattered debris. Please avoid electrical wires which are hanging loose or lying on the ground. Bring out the survival kit. Use the first aid box to help injured family members, neighbors and others. Listen to news and instructions on the wireless radio and cooperate with assisting agencies